Mine have had to, mine have pulled down to the bottom of the symbol, and they're kind of.
All right. So, we left off talking about the sample proportion. So we worked through this example. We said it's really, really similar to the sample mean. We've talked about the distribution. So it looked like something like this. We had our sample proportion. We know as long as we had a sample size over 30, it was normally distributed around whatever the true population proportion was. And then the variance of our sample proportions was, here this reflected the variance of our population proportion divided by our sample size, which is exactly what we were doing for the sample mean. So what we could then do is say something like, what's the probability I get 55 or more flips out of 100 on a fair coin? I think we worked this example kind of quick at the end. What we're thinking about here, if I'm flipping a coin, what's the true population proportion going to be? Just 0.5, right? I know if I flipped a coin enough times, 50% will come up heads, 50% will come up tails. So we're interested in finding the probability that 55 out of 100, so our sample proportion is 55 out of 100 or 0.55. And we wanted what, 55 or more? So we're looking at the area to the right. So from here, we've got a normal distribution. It's just a matter of turning that value we're interested in, 0.55, into a z-score. We said our z-score for any statistic will just be the value we're interested in for that statistic, subtract the mean of that statistic, and divide by the standard deviation of that statistic. Well, here, we know the mean of our sample proportions should just be whatever the original population proportion is. And the standard deviation would be the square root of what we know the variance will be equal to. So P times 1 minus P divided by N. So once we plug that value of 0.55 in for our sample proportion, 0.5 for the population proportion, and a sample size of what? Here we were flipping it 100 times. We'll come up with our z-score. So I think if we do that, probably I think it's 1. Yeah. Kept it real easy. We should get a z-score of 1. And now it's just like what we've been doing. We go to the table, look up that z-score of 1. The table will tell me, yeah, I shouldn't lie. The area to the left. That was bad. So I looked that value of 1 up in the table. We've done this quite a few times. We end up finding that area to the left of the probability of seeing that z-score anything lower. We wanted the area to the right. So we have to subtract it from 1. So once we get to that z-score, also it's a little bit, does that help at all? Or is that too bright? So some of you look like I just, flashlight in your eye or something. But right, once we get to the z-score, everything's going to be exactly the same as what we were doing before. Really, like nothing procedurally changes at all. Any questions on this one? Yes, I know we kind of went through a little bit quick towards the end. So let's say I won't use this one for an iClicker, but it would be a good one to go back to make sure you know how to solve that once we kind of get closer to that second example. So what if I had the same example, but I wanted 66 out of 144 coin flips or more? Well, this is where we start drawing things out. Hopefully, it can prevent us from making some pretty easy mistakes. So we've got a situation here where I'm thinking about the distribution of my sample proportions, and I've got a sample size over 30, so it's normally distributed. What should the mean of my sample proportions be here? Well, we usually don't know this, but with flipping a coin, we know if it's a fair coin, it should just be 0.5, which was, actually I should write it this way. The mean of my sample proportions is the population proportion, which for a coin flip we know is 0.5. If I want the probability of getting 66 out of 144 or more, what sample proportion am I interested in? So sometimes we're not directly given our sample proportion, we have to calculate. But if I know I want 66 out of 144, just dividing 66 by 144, that's going to be the sample proportion I'm interested in. Anyone wants to help me out because I don't know what they're about to talk about.
4, 5, 8, 3,
0.458. We'll go with that. So 0.458 is the value I'm interested in, and I want to know what's the probability I see that for anything greater. So automatically, what do I know my probability has to be greater than? 0.5, right? The area to the right of the mean is 0.5. So I want the area to the right of the mean plus a little bit more. So it's going to be something over 0.5. So right away, we've got what? B and D are the only possible answers. Now, this is where when we start dealing with proportion, it's a lot harder to kind of guess because we're always going to be pretty close to whatever that mean is, right? We're only, what, 0.42 away? But 0.42 is a lot if my standard deviation is 0.01, right? That'd be 42 standard deviations. So a lot of times with these proportion ones, I think it makes sense to just to visualize and sort of think what we're doing. Calculate the intermediate value here, right? Before in that z-score equation, remember that denominator represents the standard deviation of my sample proportions. But if I do it all at one time, I'm never seeing that. It's like built into that z-score formula. So here, if I do 0.5 times 1 minus 0.5 divided by 144, approximately what do I get there?
0.001736.
0.0017?
Yeah.
And I said we were what? 0.042 away. So we're quite a few standard deviations away. So I'm thinking this is probably going to be something that's closer to.
I apologize.
Is that wrong?
I need to square root it.
Oh, yeah,
Sorry.
that's okay. So if
It's 0.0416.
okay, so that makes a little more. So 0.0416. So I'm almost exactly one standard deviation below, right? So, we might not be, so if I'm mapping this out, right, and I calculate how many standard deviations away I am, well, here these numbers are pretty easy. I can see I'm approximately one standard deviation. I could have plugged everything into my z-score equation, and I would have come up with the same for the z-score of negative. So that's pretty far away. I mean, not as far as being two standard deviations, we said that's very unlikely. So if I was guessing here, I'm thinking, I'm at least a standard deviation away from that mean. So I'm starting to get further and further from that probability of 0.5. So I'm probably a little bit closer if I'm looking at the area to the right here. I'm actually probably a little bit closer to seeing 1 than I am to seeing 0.5. If I had if I saw something that was like negative 0.2 as my z-score, well, then I'm starting to get an area that's just a little bit over 0.5. But the further away I get from that mean, the area to the right is going to be getting closer and closer to 1. I probably would guess B, but to be safe, I'll look this up in that standard normal table. I get 1.587. I wanted the area to the right, so I have to subtract that. Now, the only reason I know that is because we just did an example where I looked up +1, and I said the area to the right of +1 was 1 minus 0.8413. We went back, that was 0.1587. So if I went the area to the left of -1, I knew that if I went to the table, I should be finding that exact same value. Now you can prove it to yourself, like go to -1.00. Sure enough, you'll see that it's 1.1587. You want the area to the right, so you have to subtract it. So we got all that work right. Any questions on it? Does that make sense? I know I'm going through this a little bit quick, but really the only tough part of this is, I think with proportions, the toughest part is just dealing with smaller numbers. We're always dealing with decimals. So it's a little bit easier to get mixed up with what my sample proportion is and what my probability of seeing that z-score is or something lower. Other than that, the procedure is really the same. Okay with this? So this is where I need to make sure I'm doing a good job of introducing this next topic, because we're going to use it for a lot of different examples. And the idea behind what it represents is pretty important for a lot of the rest of what we're going to do in this class. So I think I mentioned when we were looking at sample means, that when I take a higher sample size, right, because that variance of my sample means is the original variance of the data I sampled from over my sample size. When I was increasing my sample size, I was decreasing that variance. So if I'm decreasing the variance of my sample mean, it's becoming more peaked, right, around whatever its mean is. So it's guaranteeing that if I'm only seeing one sample mean, I think we'll go this way. So I have, let's say I had a variance of my sample means that was 10. I then take a higher sample and it drives that down to 1. And I should have used a different color here. So this is red, right? What that's going to do is it's going to make the distribution of my sample means more peaked, which guarantees that the values surrounding the mean are going to be more likely for me to see. So how likely or unlikely certain values are, kind of hard to determine, because when I know the population mean, well, then I could come up with those. But if I don't observe the population mean and all I have is my sample, well, it very well could be that my sample mean, even though I had a low probability of seeing it, maybe I saw something way down here on the distribution, right? I know that that wouldn't be the most likely sample mean for me to see, but it could be the one that I saw, and I only have one sample more often than not. So what we're going to try to do is say, look, we took a sample. Based off that sample mean, I can tell you with a certain percent of certainty, right, that the true population mean is somewhere within this range of values, right? So that we're going to look at the sample mean that we see. We're going to go a certain amount below it and a certain amount above it and say, look, I know that this sample mean may not be correct, right? In fact, I know that it probably, this is a little bit hard to think of. What would be the probability that I get a sample mean that's exactly equal to the population mean? Remember, this is a continuous distribution. So the probability my sample mean is exactly equal to the population mean would actually be 0. I might be really, really close, but that, I almost know that inherently built in, my sample mean, the probability it's exactly equal to the population is 0. Right? But if I took a really high sample, if I have 1,000 people and I calculate their average income, I'm going to be a little bit off, but I could probably tell you, if I take a sample mean and I see that the average income of that sample of 1,000 people is $50,000, it's not very likely that the true average mean is $120,000, right? Now it may be 55,000 or 48,000, right? It's probably could be a value that's pretty close to that sample mean I found, but it's very unlikely I'm going to see something that far away. So what I'm going to do is say, based off of my sample, I can create a range of values where with a certain level of certainty, I can tell you the true mean is somewhere in between this range of values. Right? So how far below and how far above that sample mean are we going to go, right? How do I choose that W? Okay. So we're going to use the only thing we have, which is our sample statistic, our sample mean. We're then going to create a range of values around that and say, with a certain level of confidence, I can tell you the true population mean is within this range of values. Okay. So how do we choose that W? Well, we know that the sample mean is normally distributed. Okay. So if we wanted a 95% confidence interval, and that's what we're going to start calling these ranges of values or confidence intervals. What we could do is say, okay, look, I know that the probability that I'm 1.96 standard deviations below, excuse me, that true mean would be 0.025. So I know that if I'm looking at the distribution of my sample means, that if I went 1.96 standard deviations, and it has to be the standard deviation of the statistic I'm looking at, right? My sample mean distribution. Well, if I'm 1.96 standard deviations below, that's a z-score of what? 1.96 standard deviations below the mean should just be a z-score of, what is z? Negative 1.96, right? Z-scores represent the number of standard deviations away I am from the mean. So I go to my table. I can prove this to myself that if I go 1.96, 1.96, okay, the area to the left is 0.025, okay? So if I go 1.96 standard deviations below the mean, I know that this area is 0.025. And if I went 1.96 standard deviations above the mean, this area would be 0.025. So I know there's a 95% chance that I see a sample mean. If I'm only going to take one sample, there's a 96% chance I'm seeing something that's in between 1.96 standard deviations above and below, whatever the true mean is, even if I can't observe it. So there's a 95% chance I see something within 1.96 standard deviations above and below that. You okay with this idea? Okay, so I know that if I build confidence intervals around, how do I want to show this to you? So let's say, thinking about here, if I saw a sample mean value that was right here, and I go 1.96 standard deviations above and below that sample mean I see, think about it this way. I don't even have to know what that mean is, but if I know the standard deviation of the variable I'm sampling from, I can determine what the standard deviation of those sample means are. So whatever this distance is, if I use that as my W in the previous slide, and I say go take that sample mean and subtract 1.96 standard deviations, and then I take that sample mean and I go above it 1.96 standard deviations. Well, notice if I see something, if I do see a value that's over here to the right, and I go 1.96 standard deviations, I'm never going to get back to this point, right? Because I'm 1.96 standard deviations below here, and I'm less than 1.96 standard deviations away from the mean for any values in this range. So anytime I see a sample mean that's in this range, by going 1.96 standard deviations below it, it will always be capturing whatever that true population mean is. Because even if I saw this as my sample mean, now when I go 1.96 standard deviations below it, I'd be exactly at whatever that true population mean was. Same kind of idea if I saw sample means over here. Well, now because I'm going 1.96 standard deviations above it, my confidence interval for any value here would always be including that true population mean as well. So anytime I see a sample mean here, if I add 1.96 standard deviations to that sample mean, when I subtract 1.96 standard deviations from that sample mean, I'll always have a range of values that includes that true population. Now, if I see a sample mean way out here, and I go, it could be, I should draw this over here. And I go 1.96 standard deviations above that value, that might not get, now that won't get me back to whatever that original population mean is. So for any sample mean in this range, by adding 1.96 standard deviations to it and subtracting 1.9, I'll have an interval that includes the true population mean. For any sample mean I see out here, my confidence interval wouldn't include the true population mean. But I'm okay with that because I know the probability I see a sample mean out here is only 0.05, right? Or has a much lower probability than seeing a sample mean in this range, which I know is 0.95. So what we're going to do is, whatever percent confidence we want to say something with, in this situation, right, if I'm taking sample means, I know that 95% of the time, if I take a sample mean and add 1.96 deviations, subtract 1.96 deviations, every sample mean in this range will include, I'll have a confidence interval that includes a true population. So 95% of the time, if I'm taking, like let's say I just keep taking samples over and over again, and I keep building these confidence intervals. 95% of the time, I'm going to end up with a sample mean where my confidence interval includes that true population mean, if I was able to actually observe it. And then 5% of the time, I'm going to end up with these sample means out here where my confidence interval doesn't quite make it back, right? It doesn't quite include that true population mean. So with 95% certainty, if I only see one sample mean, I know there's a 95% chance that the confidence interval I've created includes that true population. Now, there's a 5% chance it doesn't, right? But I'm not saying it with 100% confidence. I'm only saying it with 95% confidence. And then if I wanted to say something with 90% confidence, right, maybe a lower level, if I'm using a confidence interval, like if we put some actual values to this, it might be something like with 95% confidence, I know that the true mean is somewhere in between 100 and 200. Right? So I can say with 95% confidence, somewhere in between 100. If I want to say it with 90% confidence, I'm just going to tell you a smaller range of values, right? If there's a 95% chance it's in between 100 and 200, well, maybe there's a 90% chance it's in between 120 and 180, right? I just made the range of values smaller, so it's less likely that I see, a sample mean within that range. So if instead of 95% confidence, I wanted to change this to 90, well, all I'm really saying is I'm just going to decrease the range of possible sample means that would have a confidence interval that includes the true population. So how can I do that? Well, I just won't go out 1.96 standard deviations. I'll go out a different number of standard deviations. So let's say now I want 95 or 90% confidence. What would the area in my tails be? So I'm wanting to choose a value such that when I go that many standard deviations, so I'm trying to find a z-score here, so that when I go that many standard deviations above and below, I know that there's a 90% chance I see something in that range, which means the probability I see something outside of that range would be what? 0.1, there's two sides, right? I'm looking at the same value above and below, and so 0.05 in each one. Well, now what do? I'm using the inverse transformation, essentially, not inverse transformation, but the inverse process. Look up that 0.05, the probability that I want in the middle of that table. Find the corresponding z-score. If I'm remembering correctly, is that 1.65? 64, yeah, in between 1.64 and 1.65. So now that is how I build my 90% confidence interval. Instead, I take the sample mean, I go 1.65 standard deviations above and below, create my kind of what we call upper and lower bound on my confidence interval. But yeah, really we're using the inverse process there to look up the z-score that gives me whatever area I wanted outside of that range divided by 2. So I have two tails, right? Two sides of my confidence interval. Another way that we'll reference this is, let's see what's on this next one here. We'll call it alpha. Okay? So what alpha will represent to us is the total area outside our confidence interval. So with my 90% confidence interval, I was saying my alpha, or the total area in the tails here, or the total area outside my confidence interval, would be 0.1, which means how much would be in each tail? Alpha over 2, or 0.1 over 2. So really the z-score that I'm looking up here would be the z-score that gives me alpha total in the tails, right? But that would mean that there will only be alpha over 2 in each tail. That, any questions on that? That wasn't necessarily should be the most clear thing at this point, but. So alpha is going to be the total area outside our confidence interval, right? The total area in each of these tails, which means we want half of alpha in each tail, which now I know the probability in the tail that I want. I'm going to work in the inverse to then find that corresponding z-score. Once I have that z-score, come back to this. Once I have that z-score, it gives me alpha over 2 in each tail. Well, now I just build my confidence interval around the sample mean I saw. I add that z, this is the number of standard deviations away I want to go. So if I want to go 2 standard deviations away, well, I need to multiply that by whatever the standard deviation is. Right? So I'll add what we end up calling the margin of error. So that z-score times the standard deviation, that's what we're going to call our margin of error. I'll add that margin of error to my upper bound, and I'll subtract that margin of error to my lower bound. That's not technically correct. You should only use margin of errors once we get to talking about proportions. But for the sake of conversation, I'll reference this as our margin of error. Just makes it easier than like every single time saying, well, then we'll add our z-score that gives us alpha over 2 in the tail times the standard deviation of our sample means. We're going to give it kind of that title of margin of error. Questions here? So, I mean, based off what we've done in the past, we should be able to look up these z-scores relatively. I mean, we're using the inverse process. This standard deviation, in practice, when we actually calculate these confidence intervals, what this is going to look like, unless we want to break it down into parts, which by all means we can, like I can calculate that standard deviation of my sample means and then plug it in, or I can do this all at one time, where we know the standard deviation of our sample means is the square root of the original variance of the data we sampled from over my sample size. All right, so that's in practice, like probably going to be the version of the confidence interval we actually use. Right? Now we can calculate this ahead of time and then plug it in so that it's more simple. However way is really easier. Like every person might find it easier to do it a different way, right? But really either of these one end up giving us the same answer. When I was talking about alpha, we're typically going to kind of keep it the same. Initially, maybe some of the problems, stuff we worked through, I won't have kind of these benchmark values just so we get used to saying like, I can really do whatever level of confidence I want. For, the kind of normal convention is to do these 3 benchmark values, which would be 90, 95, and 99% confidence, which correspond to alphas of 0.1, 0.05, and 0.01. Okay. So we can work in either direction, right? If I know that I have alphas of 0.01, 0.05, and 0.1, that corresponds to 99, 95, and 90% confidence. If I've got 99, 95, and 90% confidence, that corresponds to alphas of 0.01, 0.05, and 0.1. I mean, work in either direction. I would say the easiest way to think about alpha, this is like not the most technical way to say it. It's the area outside of your confidence interval, or the percent, like if you look at the 99% confidence level, it's the percent not in your confidence interval in decimal form. So if I got the 99% confidence, 1% would be outside my interval. In decimal form, that's 0.01, that's my alpha. 90% confidence, there's be 10% outside my interval. In decimal form, that's 0.1. So that's kind of an easier way, I think, to kind of give that definition to alpha. So if we think about this equation we have for the confidence interval, what starts to change how wide that confidence interval is? So I'm going to leave this here, and we'll think about what are we have 4 things here, right? We've got my sample mean, the original variance of data I sampled from, sample size, and then this z-score. So 4 things could change. So what happens if my sample mean changes? What does that do to my confidence interval? That's just going to I'm building my confidence interval around that sample mean. Right. And let's say I see a higher sample mean. What's going to happen to my confidence interval? It's just going to shift, right? Yeah. Right. My lower and upper bound will just kind of shift as well. What if I am sampling from a variable that has higher variance to begin with? What's going to happen here? my confidence interval is going to get. So that variance in the original variable I sampled from goes up, what happens to my confidence interval? This number gets larger. What happens to this fraction? It gets larger. So now when I multiply my z-score by a larger number, I'm going to be adding and subtracting a larger value to that sample mean. So what happens to my confidence interval? It gets, yeah, and get wider. So the rest of the things we'll talk about are all things that affect the margin of error, right? All three of these components are in my margin of error. So if it makes that margin of error bigger, it widens my interval. If it makes my margin of error smaller, it narrows my interval. So what if my sample size goes up? Denominator is getting larger. So this guy here is getting smaller. The margin of error is getting smaller. I get a narrower interval. What if I want to say something with a higher level of confidence? So if I want to say something with a higher level of confidence, maybe go from like 90 to 99% confidence. Now, intuitively, if I want to say with 90% confidence, it's in between these two numbers. And then I say, okay, with 99% confidence, it's in between these two numbers. What am I probably giving you? A wider range of values the second time. So intuitively, we know it probably, as I want to say things with higher levels of confidence, it's going to widen my interval. But how does that operate? Well, if I want to say something with a higher level of confidence, that means I'm going to have to make this area larger. So the area outside my interval, or alpha, is getting smaller, right? Going from 90 to 99% confidence, alpha goes from 0.1 to 0.01. So saying something with, maybe this is, I'll write this down so we can kind of follow this one. If I want to say something with a higher level of confidence, that's going to decrease alpha, right? It's going to decrease the area outside my interval. So if I'm looking up a smaller area in my tail, if I think about a z-score, if I wanted 0.1 in that tail, I'm going to find that z-score. What if I wanted 0.01? I know that my z-score is going to become, now this is where it gets a little harder. When I look up these values in my table, if I just look up alpha over 2, I'm always going to be finding what sign of my z-scores. These are all areas, alpha of 0.1, 0.05 to 0.01, all areas less than 0.5. So I'm actually going to be finding negative z-scores. But that negative sign is already built in to my confidence interval equation, right? I go use the negative z-score to get my lower bound, and I use the positive same value of that z-score to get my upper bound. So I have to remember that when I look that up, I really just want to, like, I can kind of ignore the negative sign, right? When I'm thinking about the magnitude going from 0.1 to 0.01, right, that's smaller alpha, my z-score is actually going to become larger in magnitude. It's actually less because it's a larger negative value, right? But it's becoming larger in magnitude. So this smaller alpha, in order to get a smaller area in the tail, I have to go out more standard deviations away, or my z-score for alpha over 2 is going to be getting higher. If the z-score for alpha over 2 is getting larger or higher, I'm widening my interval, right? Which matched up with our intuition. If I want to say something with a higher level of confidence, I got to give you a wider range of values, right? So that's kind of how that operates, though, not just using our intuition. Any questions over anything? I think I've got a slide here where it matches up all those. It says them all specifically, like as they all get larger, but we can work in either direction, right? So if a larger alpha, right, means that we actually want lower confidence, and we'll actually say smaller interval. We were kind of talk through what happens if I wanted a higher level of confidence, which would mean a lower alpha, and kind of instead of doing a larger sample size, if we wanted to, we could do a smaller sample size. But this is all kind of phrased in terms of if they all got larger. Any questions on this one? We're out in time. All right. Let me decide what I want to do today. So we could work through some examples, which I think would be good. So let's do an example here. And then I think I'm going to show you, I'm going to come back to this, like when things would change. But I just want to have an example so we have some numbers to work with first. So let's say I have this original variable I'm interested in, which is the length of a pregnancy. And the variance is 9 weeks. So it's going to start out a little goofy. So all these examples, the whole reason we want to build a confidence interval is because we aren't able to actually observe what that true population mean is. All we have is our sample. So it's going to seem a little weird at first, but we need to use this as like the base level of understanding, and then we'll add in something that's like more like real life, I guess I would say. But let's assume for now, we don't know the population mean, but somehow we know the population variance, right? And this isn't the most impractical for a lot of situations. Like a lot of the times if we have a production process, we know that the machinery that's being used, like there is a known variance on what it's producing. Like, so if I'm making, I don't know, choose anything, I think the example I use later on is like a hockey puck, right? Whatever the machinery is that's used to produce these, I know that it won't produce the exact same weight for each hockey puck. And there's actually going to be a variance that's like built into the machinery. So as long as I know that, even if I don't know what the mean weight is set at, right, I can use that known population variance. So I've got a population variance of 9. I know that if I sample, I'm sampling 81 different births or infants, and I find the average length of the pregnancy or the gestation was 38 weeks. So if I wanted to build a 95% confidence interval where I could say the true length of a pregnancy is somewhere within these two values, right? Between this lower bound and this upper bound. So how would I start tackling this? Well, I know that my confidence interval equation is going to look something like this, where if I wanted to, I could substitute in the equation for my standard deviation of my sample means to be the square root of my of the original variance over my sample size. So really, I could just start out plugging things in. What sample mean value did I find? From my sample of 81, I found 38 weeks. The original variance on the length of a pregnancy I was told was 9, and I sampled 81 births. So really all it is at this point is just plugging in the values that we were given. Now in practice, we probably calculated this mean ourselves, right? But that's really the only difference, rather than just being told what they are. We would have to be told, or we would have to know what the population variance was. Like we don't have the population data. If we did, we would just calculate the population mean, right? This is coming from something. This is either being told to us, or like I said, it's a known variance on the production process of a certain thing. So we just plugged in everything that we kind of knew. The only other thing we need to do is find out how many standard deviations away from this sample mean value of 38 that I saw, how many standard deviations away do I want to go to ensure that my confidence interval, I can say with 95% confidence, includes the true mean. So if I want 95% confidence, what's my alpha there? Right, so what is alpha? I know my 2's and alphas look similar. I apologize. 2, right? What would my alpha be for the 95% confidence? Yeah, right. It's the percent outside my interval in decimal form. So 5% is outside of my interval in decimal form is 0.05. Right? I'm thinking about the visual that I'm doing there. I'm saying that the total area in my tails here is 0.05. So it must be that in each tail, I've got half of that, or 0.025. So if I go to the table, I look in the middle of that chart and find the value that's closest to 0.025. I end up finding 1 z-squared. You look in that table, you go to the middle, you find 0.025, 1.12. We actually already used it, but if sure enough, you go through, find 0.025, go over and up to the row and column headings. We know that the z-score we want, we'll find negative 1.96, but I said that positive negative is already built into our confidence interval equation. So we just want to plug in the value of 1.96 here, right? So we go through, got all these different range of possible values. They all look reasonable. One thing that we can do, kind of rule out some answers sometimes, although I don't think I've made it easy in this case, is my confidence interval not only should include the sample mean I found, right? If we remember what we're doing, we're building the confidence interval around that sample mean, but we're going the same distance above and below it. So not only should it be in my interval, but it should be smack dab in the middle, right? It should exactly be in the middle of my lower and upper bound of my confidence interval. And this is typically how we'll write confidence intervals. Kind of using these brackets, putting what that lower bound on the confidence interval is, comma, or sometimes I'll use a semicolon here, and then what's the upper bound of that confidence interval. So we go through, we found that z-score. We could do an intermediate calculation here. So instead of plugging everything into this equation all at once, I can come up with this ahead of time. So I calculate that ahead of time, I get it's 1/3. So now I plug in 1/3 here. So 38 plus 1.96 times a third, that's my upper bound. 38 minus 1.96 times a third gives me my lower bound. So if I end up doing that, I'm going to build the values of 37.35 and 38.6. Any questions on any part of that process? All right, so what I want to show you. So one thing that's floating around in the background here. So I think about the distribution of my sample means. We said we don't know what the true population mean is, but the standard deviation we just found was 1/3. Right? So what I'm doing with my confidence interval is I'm going a certain number. In this case, if I want a 95% confidence interval, 1.96 standard deviations above and below. So 1.96 times a third above and below. Well, what happens if instead of 81 infants here, let's say I sampled 200? What's going to happen to the distribution of my sample means? Well, I'm looking at a higher sample size. So that's going to increase n. So that'll decrease the standard deviation of my sample means. So what that's really saying is it's going to become more peaked. So now, if I want to go 1.96 standard deviation, I still want to create this 95% confidence interval. My standard deviation, I still want to go the same number of standard deviations, but my standard deviation here should be much lower. I don't know. I'll say it's 110. I don't know what it actually ends up being. Well, if this becomes much lower, what's going to happen to my confidence interval? With a higher sample size, I'm still going the same number of standard deviations away, but the standard deviation is significantly lower. So I can keep the same level of confidence, but with a higher sample size, I can give you a much narrower range of values, which is really important. Like if I'm trying to say, what's the concentration of like, I don't even know, something that's like purple, arsenic or something. Like, actually, this is a good example. I used to work at a lumber yard, and they have treated lumber, and there's arsenic, I think it's arsenic, actually in the treated lumber. It's like green lumber, you can see outside. But like, you don't want the arsenic level to get above a certain point where it's very damaging to whoever's handling, right? Well, if I only take a sample of like 10 boards, and I build this confidence, well, oh yeah, the true level of arsenic is somewhere in this range. Right? Well, if I can sample a much higher number of boards and then tell you like, I'm using the same level of confidence, but because I took a higher sample size, the standard deviation is so much lower, I can really pinpoint down exactly the level of arsenic that's in these boards. Before I gave you this huge range. Well, if I'm trying to make decisions and you tell me, oh yeah, the range is from, I don't know, 1 milligram to 500, Okay, well, I mean, that's a pretty wide range of values. But if I can get these really high sample sizes and narrow that down, to like, well, actually, I can tell you it's somewhere between like 120 and 134. Where I can really be able to pinpoint down where that true mean is and make a lot more useful decisions moving forward. So that's why, and I think I kind of alluded this last week, and I started here trying to refresh our memory, but these higher sample sizes are almost in everything we do always a better idea. And it makes sense. If I just have a bigger sample, that sample should be a more accurate kind of reflection of the population. All our biases, as long as we've taken care of all of those things that we talked about. That's why taking a higher sample size really pinpoint and narrow down this range of values. And what that's really operating through is things that we've already talked about with that distribution of sample needs. Okay. All right. I think we'll walk through this one together, and I'll have another example that maybe we'll kind of start out with on Wednesday, that I'll have you do. So I don't think I mentioned this in class, but I know dialogue days are going on this week. If you want to attend one during this class, I'm not going to penalize you, but we're still going to have class. So we'll still meet. If you really want to go to one of the ones that's at this time, I won't use the iClickers on Wednesday. So we'll go through some potential questions, but I probably won't use the iClickers again until Friday. Okay. Questions on that? Just make sure I was clear on that. Okay. So one thing that's kind of interesting, I'll go through this example a little quick, but I want to at least allude to the usefulness of confidence intervals a little bit as well. So let's say I went over to the rec center and I grabbed 35 different 45-pound weight plates. Right? This might seem like a really dumb example at first, but I measure all of them and I find that from these 35 plates, the average weight is actually 46.5 pounds. So when they're pouring these weights, right, there's a bunch of different metals that all have different weights. Not every pour is uniform. So some of them end up being a little bit heavier. Some of them end up being a bit lighter. From the sample I took, I found that the mean was a little bit higher. Maybe it's just that I ended up with a few more of the weights in my sample that were from the right side of that distribution. So I want to build a confidence interval. So I'm going to do, I've got the original variance on the production process, right? I contacted maybe the manufacturer and they told me, we know that the weight varies because of the pours aren't uniform. And based off of our kind of knowledge of that machine, the variance is 25 pounds or a standard deviation of 5. If I wanted to build what confidence interval, so if my alpha is 0.1, what level of confidence would my confidence interval be? Yeah, so there'd be 0.9 in my interval. When we talk about confidence levels, we usually say with percentages, so 90% confidence. Now, if we look at these, right, 46.5 looks like, sure enough, it's in all of the, actually, we can rule this one out right away. 46.5 isn't even in this confidence interval. That doesn't make any sense as a possible answer. Right? My sample mean should be exactly in the middle of my confidence interval. I'm adding and subtracting the same value to it. So I want to find kind of what this is. I'm running out of time here. The first thing I would do is look up that z-score. So alpha here is 0.1. So alpha over 2 would be 0.05. So I look up 0.05 in the table, find the corresponding z-score, go over and up and find it's 1.65. From here, it's really, I calculate the intermediate step, find that standard deviation, plug all my values in to get my lower and upper bound. I'll add that margin of error to my upper bound. I'll subtract the margin of error to get my lower bound. So I'm kind of going through this quick, but I just want to make a point before we leave. So if I'm looking at this confidence interval, I can go to that manufacturer and say, look, based off the sample I took, right, your weight plate that you're claiming is 45 pounds, with 90% confidence, I can tell you the true mean of what you're producing is not 45 pounds, right? It's somewhere in between 45.11 and 47.89. Now, that seems trivial when we're talking about weight plates. But if I go to, if I'm thinking about measuring something like steel beams that are supporting, a building or something, well, yeah, this is really important to be able to say, like, with this level of confidence, I can tell you your product is not the weight you're saying it is, and that's an issue, right? You also apply this to light drug manufacturers, right? Whatever you're saying is in that drug is not, right? It's not meeting the level you need it to meet. So we literally could use confidence intervals to like save lives. Right? I might have went really extreme there, but it really is, you know? So we will meet again on Wednesday. We'll kind of continue to do some work with confidence intervals. I'll probably do a little bit in Excel. So if you do like to work along, make sure you're bringing your computer for that. Otherwise, I'll see you guys on Wednesday, okay?